Our lesson today is a continuation on the bigger manifold of calculus, and our topics of interest today, product spaces and homomorphism of a VW, or in short, we just say hom VW. So these are slightly abstract concepts, and I'll try to build into them slowly, and I hope by the end of this interaction or lesson, we would have understood what product spaces are, what a homomorphism of VW or vector space V into vector space W means. So let's dive into this. If you have any questions, and if you want further explanations, we welcome your questions, we welcome your suggestions, we welcome any interaction that you'd like to have with us. So let's start. We have a set A that constitutes of elements A1, A2, all the way up to AM, right? And then there is a set of functions F that are able to take any of the elements within this set into a vector space W. So we would name a set of all functions F that transform elements in A, could say any elements in A into the vector space W. And that set is usually denoted as W to the A. An example would be, let's say if you have a vector space, a set A that is transformed into a real number. Now this is not a vector, but how we would represent a group of functions that do that job is the real number, or R to the A. So this is just an introductory remark, but let's summarize this into something more concise. We said something. We did come up with a notation, and that is a vector V equals, or a vector space V equal to W to the A is a vector space of W valued functions on set A, right? So in other words, we have this function that transforms set A into vector space W. Now, there are these amazing laws that we deem to hold in a vector space. So one of them is the associative law, where if, let's say, you have function f, g, and h, and then you have f and g grouped together, and you're adding that to h, that's the same as saying f plus g and h grouped together. So that holds in the vector space W to the A. And it does so because those functions would normally bear the same, they do obey that law in the vector space W. Now, previously we saw that we did have a coordinate functional, and the coordinate functional here, when applied to a vector to a a space or a set of this function, it extracts, it reads off the function at coordinate I. So it's an evaluation at I. Now, this is when we have a functional. In other words, you have this function that you feed it with vectors and it coughs out a real number. But what if the output is also a vector? So for the vector counterpart of the coordinate functional, the mapping may be from a vector space V to a vector space W, right? We call it a coordinate or the ith coordinate projection instead of functional. So this is important. It's just a terminology thing that we are looking at here. For functionals, it will be a coordinate functional. For the vector counterpart, we have the output is a vector, and we'll call it a coordinate projection. Therefore, the same thing happens here. The coordinate or the evaluation at J can be expressed as pi j of the group of sets F, the group of functions F, or projections rather. So this is the jth coordinate of vector F. So F consists of several elements in that, vector elements, and so the jth one can be extracted, can be read off by applying this expression. Now the vector analog of the Cartesian n space Rn, and Rn here is used to denote a tuple, an n tuple of n elements that are real numbers, but the counterpart on the vector side of thing is usually a set w to the n, yeah, and this is in vector of all n tuples alpha, where alpha 1 is a vector, alpha 2 is a vector, all the way up to alpha n, and all these vectors in this tuple belong to the vector space w. So sometimes it's also expressed as just w to the n. There's no bar to it. Okay, and then obviously from this, alpha j is the jth coordinate of the n tuple alpha. So that these are pretty straightforward concepts. I hope these are clear at this point. So let's look at a group of vector spaces W1, W2 up Wn, which is a set of, for all n tuples, alpha consisting of alpha 1, alpha 2, alpha 3, after alpha n, such that alpha j, j being an index, is an element or a member of wj, for j equals to 1 all the way up to n. So a collection of these vector spaces is also a vector space. And there's how we tend to group this. There's the concept of the Cartesian product. The Cartesian product, which we had looked at earlier on, is expressed as shown here. This is also a vector space of vector valued functions. And one way of looking at a Cartesian product is, for example, right, if you have a line, right, and the coordinate notation is usually a number, a real number, and that is, let's take that to be x, and then now you add a y-axis. That's another line with a coordinate notation that is in real numbers. So any point here is a member of the R, any point on that single line. But as soon now we have a two-dimensional point, now we have the Cartesian product, right? So the points in the two-dimensional space denoted by I are now elements of that Cartesian product of a set of two sets of real numbers. And obviously, as you go to the higher dimensions, if it's the three-dimensional space, now that becomes R cube. Now, obviously, these are not vector spaces, these are real numbers, but just imagine these, the analog in the vector space is a Cartesian product of these vector spaces. Interestingly, just to put some definition onto paper, if vector space Wi such that I is an element, an index element of capital I, is any index collection of vector spaces, then the Cartesian product shown here, expressed here, of these vectors is defined as the set of all functions with domain I such that the ith evaluation of that function is a member or an element of vector space Wi. That is for all I being members of capital I. So let's move on. Let's move on. So let's just shift some gears a little bit. And here we're going to show just an example. So let's consider S to be a unit sphere. That means a sphere with radius of 1 in a three-dimensional space, Cartesian space. And we denote that by R to the 3 or R cube. And the formula for that sphere S, or the point representation on the surface of that sphere, is S equals to vector X such that the elements in X, X1, 2, 3, so the summation of the square of those elements equals to 1. For those of you who are used to looking at it from an XYZ perspective, X1 would probably be X, and X2 would be Y, and then X3 would be Y square, would be Z. And so the sum of the squares of those coordinate points equals to 1, or 1 squared. And so how we would draw it, this is just one quarter of, not even 1/4, it's an eighth, but one section of what we are interested in. So let Wx be the subspace, or the vector subspace on R cube tangent to S at X. Now, it's very important to know that when you're looking at a vector space, that is a plane that, or a space that at least includes the origin. And so if we have X at this point, then the plane that is parallel to the tangent at X, but that includes the origin, is what we would represent with Wx. So that the plane parallel to Wx, being the tangent, now can be expressed as wx plus x. And we saw that in our previous lessons. When you have a plane that has a parallel translation, it's a matter of just adding a number to it, or a vector to it. So wx plus x is the tangent plane, right? And we see it denoted by blue here. So a function f in the product space W equals to the product of all manner of, tangents, or planes, tangential planes that include the zeros. So the products, or the Cartesian product of Wx is a function that assigns to each point x, and x could be any point on the surface of the sphere, on S a vector Wx. So we see that there is this function f that transforms, or that takes a point and gives you the plane that is tangential to that plane, for all x's that you find on the surface of that sphere. So we now say that this function here belongs to this Cartesian product space. Such a function is called a vector field on S, right? Transforming a point, or a vector point, on the space to a plane that is parallel to the tangent at any specific point. So that's the product set W, or the Cartesian product set W, is a set of all vector fields, on S, and W is that vector space, right? W is a vector space. So that's just an example of how we can make use of the Cartesian product. So if we remind ourselves about the coordinate projection, and we see that the jth coordinate projection on this vector space, the Cartesian product vector space, consisting of all these vectors wi. So the jth coordinate projection there is the evaluation at j. So extracting, if you have these vector functions that are indexed, and you apply this notation, then you're just reading off the function, or the projection, the vector function at the jth position. It goes without saying that the natural vector operations on W are uniquely defined by the requirement that the coordinate projections all be linear. And that's very important. We'll get to see that and why that's important. We have a theorem that the Cartesian product of a collection of vector spaces can be made into a vector space in exactly one way, so that the coordinate projections are all linear, right? So that's a requirement for you to create a vector space constituting of a Cartesian product of the constituting vector spaces. The next important item that we'll be looking at is the homomorphism of VW, or hom VW. And previously we saw that if W is a vector space and A is any set, then the space W to the A of all mappings, that is F from A to W, is a vector space of functions in the same way that a transformation from A to the real number space R happens. So if A instead is just a vector V, then the subset W to the V instead of now W to the A, consisting of all linear mapping, is designated as the homomorphism VW. So here now we are focusing on the linear mappings from vector space W to vector space V to the vector space W. So that is the homomorphism that we're talking about. So one theorem that we would like to remind ourselves, or just put across, is that the homomorphism of VW is a vector subspace of the space W to the V. And what is a vector subspace? A vector subspace is that hyperplane or that region that contains the origin or contains a null point or a null space. So, and our definition of a homomorphism of VW is the set of linear mappings that transform items from the space or the vector space V to a vector space W. So imagine we have the transformations. Imagine we have the transformations T, that's the subset of the homomorphism or hom VW. And then on top of that, let's say we do have S. That's also an element of the homomorphism VW. So because any transformation that's a homomorphism of VW is going to be linear. So if let's say we say the transform that is a sum of S and T of elements X multiplied by vector alpha, and alpha, I will make that clear, where alpha is an element of V and beta is also an element of V, but X and Y are elements of the real numbers. So since this is this expression here is each individual expression is linear, this can also be looked at as X alpha Y beta plus T X alpha plus Y beta. And again, since S and T are all linear, we can say this is the same as beta plus X T alpha plus Y T beta. Okay. And as we continue, we come to, by grouping this and this is the same as S plus T alpha plus Y S plus T beta. Right? So we see very clearly that S and T is linear, and at the same time the homomorphism of V and VW is closed under addition. One other important thing is that this sum here is obviously this sum here is an element, this transformation here is an element of WV. And we see that what we're seeing here is that this result here could easily be 0, depending on how you choose X and Y. So essentially what we are seeing here is that there is a null space within the homomorphism VW that proves that the homomorphism of VW is a vector subspace, and this is a very important point about what a vector space or a vector subspace means. Another theorem. The previous theorem we saw was that the homomorphism of VW, in other words, the linear mappings from vector space V to vector space W, we saw that the list of functions in there constitute a vector subspace. There's another theorem that I'd like to also see, that the composition of linear maps is linear. In other words, if you're nesting the one linear map with another, that the result of that nesting is linear. And that is, if, for example, T is a member of the homomorphism of V in W, and S is a member or is an element of the homomorphism of VWX, then ST, the composition of S and T, is an element of homomorphism Vx. And one other thing we'd like to note is that, moreover, the composition is distributive over addition under the obvious hypothesis on domains and codomains, right? Another thing that we could play around is if you have S1 and S2, and then you create a composition with T, then you have S and 1 being composed with T, and then S2 and T, and also the same way if you have S and then you're trying to create a composition with T1 plus T2, then you could open it up, and so you're distributing that composition around. And finally, the composition commutes with scalar multiplication. So I don't need to really go much into detail about that, but we're going to do a small proof here. We're going to prove why this theorem holds, right? So the first thing we would say is that you do have S and T. S is a member of the homomorphism VW. T is a member of homomorphism VW, and S is a member of homomorphism WX. So if we say that S being composed with T, such that you have these vectors alpha and beta, and then what we have is that this is the same as S bracket T X alpha plus Y beta, and alpha and beta here are members of V, So what happens next is that, this can go in so that we can pull out the constants. These are real numbers. Um, you know, now pull that out, and so we have S T alpha plus Y S T beta. Okay. And as we progress about, we find that X is the same as, I mean, this part here, this term here is the same as X times the composition of S and T on alpha, is Y, composition of S and T on beta. And so S and T, as we can see here, are linear. In other words, you've been able to take the sum that is inside the input, and that has resulted into the sum of the output, taking in the independent input values. So in other words, the composition and T is linear. And what does that entail? Showing that if I have a function that is the same as f alpha plus f beta. If you can show that, then I think whatever you're trying to show is linear. Okay, so let's keep going. Let's keep going. So next we're going to look at a corollary. This is just simply a derivation of what we've already seen previously. So what this corollary says is that if T be a member of the homomorphism of VW, and that is fixed, then composition on the right by T is a linear transformation from the vector space homomorphism Wx to the vector space homomorphism Vx. And it is an isomorphism if T is an isomorphism. So we'll ignore that last sentence for a minute, and we say that since T is a member of the space homomorphism VW, and let's assume there is another S that is an element of homomorphism. Let's take it to be WX. So if you have a composition of on the right using T, and that takes, let's say, vector alpha, such that alpha is a member of V, then we see that this becomes S beta, such that beta is a member of vector space W, right? And since we say that S is a member of the homomorphism Wx, that means that this transformation S of B will result to gamma, where gamma is member of X. So we've seen a transformation from V space, from V to X. And that is why we have the composition resulting into a homomorphism, a space homomorphism from the V to the X space, vector space. So that's just a quick look at that. But we do have another theorem which says that if W is a product vector space W, such that we have W being equal to the Cartesian product of Wi, then the mapping T from vector space V to W is linear if and only if this pi I of t is linear for each coordinate projection, pi I. So this is straightforward. What pi I is the evaluation at the coordinate I, and sometimes we would say pi I composed with t, or composition of pi I and t is ti. So that's pretty straightforward thing. But we could go ahead and do some proving here. So if t is linear, we already know t is linear since t is a member of a homomorphism VW. Then pi I, or composed with t, is linear by just looking at this theorem here. Now let's do something else. Suppose conversely that the map pi I composed with t is linear. Then that means that pi I in bracket t of x alpha y beta, the same way we did things before, is the same as, and we can pull these things out so that first what we can go ahead and do is I would like to have just gone straight away to say this is the same as x ti pi I of t of alpha plus y pi I of t of beta, right? I would have loved to do that. And then what this means for us is that we can actually pull pi out. We can pull pi out and we say that this is xt alpha plus y t beta. And so we see that since this is linear, the sum inside the input side is linear. This means that we do have a pretty much a sum of the independent input items here. So also, if we look at this, we've taken things inside the bracket. The sum of things inside the bracket is the same as the independent sum of things. So this already proves that the coordinate projection here, pi I, is linear. So that's a straightforward thing. We could play around, but I think that is as straightforward as it could be. A couple of things we would like to see, just pushing back to what we saw previously. So like if T is a linear mapping from, if let's say T is a linear mapping from R to the n space to a vector space W. And R to the n could be, let's say, a tuple, that's x1, x2, all the way up to xn. So if we're able to transform this x to a vector space W, then it means that we do need to have a skeleton such that if we have t of x equals to some w, then that means that it involves x1 times a vector 1 plus x2 vector 2 all the way up to xn, right? And this combination of vectors here, these are what we call the skeleton, yeah, of that transformation or that mapping. So we want to pick the ith term. And the easiest way is to look at this as a matrix, right? And then we have vector here x1 up to xn, right? So the ith term of this matrix, this transfer function, is going to look like what we have here, right? Because essentially what you have here is you have, this is a column, this is a column, this is a column, and we need to get the ith row there, and that's what this thing essentially is. So you have the ith item, but you're sweeping across j equals to what, column number 1, number 2, number 3, so that you have row, and if we are to use, so I1, I2, all the way up to In. And this is the projection that we are looking at. So let's continue a little bit. If W ends up being just another tuple of m terms, r to the m, then pi I is the ith coordinate functional yi, and bj is the jth column of the matrix. So we have this matrix that we'd envisioned. So we have beta 1 all the way up to beta n, and then we have and this beta goes up to m term, right? M, beta 1m all the way up to beta nm, and here we have x1 to all the way to xn, right? And the term here will be, instead of beta whatever, we're using t I j. So we see that at the ith location, using the coordinate functional, we are extracting ti, and then the j term is the entire row. So if y is transformed to the yi time, so we are looking at the bj is the jth column, we're looking at the j, and the matrix T this matrix here is Tij of T. So this coordinate function here is simply the Tij, is the Tij term. But the skeleton here is the entire row. So in other words, pi composed with T is a linear function whose skeleton is the ith row of the matrix, as we stated. Okay. Previously, we considered vector y is equals to tx to be y is equals to, tijx to tijxj summed from j equals to 1 to n, taken by the reading off of the ith coordinate in the vector equation. Now that reading off, we applied the coordinate mapping pi I, or in algebraic terms, we replace linear map T by the set of linear maps here. So we have a set of linear maps that constitute the matrix or the mapping that we're interested in. So if let's consider a situation where we are having a linear mapping that transforms items in the same vector space to the same vector space of V. We would designate this as just the homomorphism of V, or hom V. There's a theorem which we would like to state that it means that in the homomorphism of V subspace of space, the rules of algebra hold. In other words, hom V is an algebra. And what is an algebra? An algebra is this, a relations for which if you have vector A multiplied by vector B in bracket and C, that's the same as there is associated property as regards to multiplication, right? C. And then we have, if we have A and in bracket we have B plus C, then this is the same as A composed with B and then A in composition with C. And the same thing happens for if you have A plus B in composition with C, that's the same as A with C plus B with C. And then if you have, A in composition with B, and then you have a constant, that's the same as K A in bracket composed with B. And it's the same as A in bracket K B. So all these relationships hold within the homomorphism of V. So that is it. So homomorphism of V is an algebra. And that is any vector space which has addition to the vector operations and operational multiplication related to the vector operation is called an algebra. Next thing we're going to look at is the very interesting concept. Up to now we've looked at product projections, that is a analog or vector analog of coordinate functional, but here we are now going to look at the pi I or pi j with respect to the product spaces, and then we'll also look at the injections. So Let's say taking the Cartesian product space W being equal to the product of WK, in which K is a member of the capital K. For each J, the mapping theta J takes a vector alpha that is a member of vector space J to the function in the product space having the value alpha at the index J and 0 elsewhere. So that theta J takes a vector alpha, and then what it does is it only leaves alpha at the jth position, and there is a 0 elsewhere. For example, if we have theta 2 for the space, the product space, Cartesian product space, W1 times W2 times W3, this is the mapping alpha tending to 0, alpha 0 from W2 to W. In other words, it's injecting that component into the W space. If we review, for example, if we look at the three-dimensional Cartesian space as r times r squared, then theta 2 is the mapping from this two-dimensional space to this position, or it could be equal to replacing the items we have in the two-dimensional space and plugging it into the three-dimensional space. This relationship, or this mapping, is what we call an injection into the product space. So we'll continue exploring this a little bit more. But what we need to know is that we call theta j the injection of wj space into the product space, wk, and obviously k is the index. Interestingly, if we consider capital IJ to be the identity transformation of WJ, and that means, transforming the same thing to the same thing, then since we see, or we saw theta J to be a projection or an injection, of WJ into the product, so you're creating this extended vector with everything else 0, but only leaving the WJ, the vector that is a member of the WJ vector space, and then again going ahead to use this coordinate projection that extracts only the jth item. So that means that this combination is the identity transformation, and obviously theta j, pi j in combination with theta I is equal to 0 when I is not equal to j. If k is a finite number and I is the identity on the product space W, then this is how we could also write it. So the summation of everything amounts to the identity matrix, or transform or transformation. In the case where we have a product, Cartesian product of the three vector spaces, and we have theta 2 and pi 2, so pi 2 extracts alpha 2 here, and then what happens next is that this alpha theta 2 injects the alpha 2 into the product, or the Cartesian product space, and that's with the other parts being equal to 0. The identity simply states that alpha 1 0, 0 plus 0 alpha 2 0 plus alpha plus 0 0 alpha 3 equals to alpha 1 alpha 2 alpha 3 for all alpha 1 alpha 2 and alpha 3. So just looking at a simple example here, for a simple example, considering that T is the homomorphism of r cubed to r squared. That means we have a transformation that takes something in the r cubed space and then or three-dimensional Cartesian space to the two-dimensional space. This is the same as a matrix, and we have this matrix T that is obviously going to take a three-dimensional coordinate space and then cough out a two-dimensional vector. So previously, since we saw that what the coordinate function or coordinate projection pi I of t, that's the ith row of the matrix Tij. So for the matrix that we just saw, pi 1 composed with t is going to be a linear functional whose skeleton is here. And this is the first row in the matrix of T and can be expressed as obviously when you multiply with the input vector x1, x2, x3, so we get that y1 is equals to x1 minus x2 plus x3 obtained from this transform equation. And that just goes from reading the first row. Thus, we can decompose T into two linear functionals, that is Li equals to pi I composite T, and then reassemble them such that we have L1 and L2, and more exactly, Tx, having after putting in the input, is composed of these two columns or two components, where this is considered to be L1 and the second one is considered to be L2 for all x's. Now we can present the reassembly as the action of linear maps theta 1 and theta 2. Remember, these are the injections that we talked about. L1x, L2x are considered to be theta 1 in bracket L1 x plus theta 2 L2 x, and since we know L1x to be pi 1 of tx, so we can now consider let me probably just put here and put that 2 there, okay? And this is the same as x because these are identities 1 plus identity 2, right? So which shows that a decomposition and reassembly of T is an expression of identity, this injection, and then times the projection. These mappings, when summed together, amount to the identity I that we saw previously. In more general terms, if T be an element of the homomorphism VW, and W happens to be a Cartesian product of the vector space is Wi, then Ti can be looked to be the projection pi of T, which is in the homomorphism VWI. For each I and Ti can be considered the part of T going into Wi, since Ti alpha is the coordinate projection of T alpha for each alpha. We can also reassemble the Ti's into form T again by expressing T being equal to the summation of theta, the composition of theta I and Ti, and theta I is simply that product injection mapping. Now, for the summation of of theta I and Ti, as we saw this previously, being so first of all, Ti is that coordinate projection pi I of T, and so when we express that way, we now have theta I and pi I, and we know that to amount to II, and II times T. So when you sum up everything, this becomes the matrix capital I, the identity matrix, multiplied by T, so we get T. So we've built T from T using these two mappings, the injection and the projection mappings. Now, any finite collection of Ti's on a common domain can be put together in this way to make a T, as we have seen, and we can assemble an M tuple Ti from I equals to 1 to M of linear maps on a common domain V to form a single M tuple values linear map T. Given alpha being a member in V, we simply define T alpha as an M tuple whose ith coordinate, Ti alpha, for I equals to 1 to M, and then T is a linear transform. So these are just obvious things that we're repeating, but find ourselves, we had that transform T that takes an X and was able to use the matrix that we provided, transforming a point in the three-dimensional Cartesian space for two-dimensional space, and we formed T by assembling the two linear functionals shown here to form a single ordered pair valued map. Just straightforward. We just have a quick theorem here, which is straightforward as well. If Ti is in the homomorphism V Wi for each I in a finite index set I, and if W is the product space, then the product space here is the Cartesian product of Wi and I being the index. When there is a uniquely determined T in the homomorphism VW such that Ti is equals to the product of, the composition of the coordinate projection and the transform T for all I in I. So we've already seen this. Ti is the same as pi I composed with T. We can decompose a linear transform mapping T whose domain is a product space V, which is a vector Cartesian product of Vj, j from 1, j equals to 1 to n, into the maps of Tj equals to T, composed with the the injection, the product injection with domains Vj, and then reassemble these maps to form T by the identity that we see here. So we can do some acrobatics here and there, but these things are straightforward. We'll keep moving forward. One theorem that follows from what we've really looked at, it says that if Tj is in homomorphism Vjw for each j in a finite index set J, and if V is equals to the Cartesian product of Vj, and then there exists a unique T in homomorphism Vw such that the composition of T and theta j equals to Tj for each j in the capital J domain. So what essentially Tj is just transformation of any item, alpha j to an item beta such that alpha j is a member of Vj and beta is a member of W. And this unique linear mapping that definitely belong to the jth, alpha jth, belonging to Vj is Tj, and that builds up this unique T in the homomorphism Vw such that when you use the product injection, you can extract Tj out of T, right? Where T is an alpha and beta, something like that. Okay, so that just brings us to the end of this prolonged treatment of things. I hope you did enjoy what we did here. It was protracted, but I think there's some interesting concepts that are interesting and informative. If you have any question, feel free to just reach out. We'd love to chat. We'd love to grow. We'd love to get to understand these aspects of vector spaces, specifically looking at product spaces, but also looking at the homomorphisms. Thank you until next time. Bye bye.